Hey, welcome to some notes on universal gates using the NAND gate. So this is our first time covering this concept of a universal gate. Let me kind of start filling this in. First, we're going to cover. We're going to talk about what a universal gate is in a second. But first, let's just get down what a NAND gate is. So a NAND gate is an AND gate, and the AND gate symbol looks like this. It's kind of like a rectangle on the top, the bottom, and the left, and then a semicircle on the right, and then the N in the front really is for the inverter. So it's a AND with an inverter. It looks like that. Okay, and a 2-input NAND gate. All right, it's going to have 2 inputs there. We'll call them X and Y, and then our output is going to be Z. And if you think about tracing X and Y through an AND gate, we get X and Y like the product. Okay, but then through the inverter, the little circle means it's an inverter. We've got the inversion, or not, X and Y. And then because of De Morgan's, another way that we could write this, it's the whole break the line, change the sign. We could have X or Y, really not X or not Y. Okay, and this is going to have a truth table that is the exact opposite of the AND gate. It's the AND gate inverted. So an AND only had a 1 when we had both 1s, right? And then everything else is 0. Well, this is the exact opposite, where we will have all 1s and then a 0 there. Okay, now the idea of a universal gate means that we're going to use this one gate. We're not going to use inverters, ANDs, ORs, our traditional 3. We're going to be able to use just a NAND gate to create all of the logic, all of the regular AOI and or an inverter logic that we could have before. Now we have to be creative in how we use these NAND gates. So someone discovered that if we use the NAND gate in certain configurations, we can produce the exact same logic. So the first one we'll cover is the idea of an inverter. So an inverter normally just simply switches the sign, and our classic inverter was this, right? If you can see that. So instead of, I'll zoom in a little bit. Instead of using this inverter, we're going to have our value, our input, branch and go into a NAND gate twice, and that becomes equivalent to not X. And if you want to trace that to try to make sense of it, think of, you've got X coming in, so this is branches, these are both X, and kind of right here before the inverter you would have X and X, or the product of X and X, which through our Boolean algebra is the same as just X. And then after going through the inverter we would get not X. Okay, so if you want to write a truth table here, if we plug in a 0 we're going to get a 1, if we plug in a 1 we're going to get a 0. Alright, so the idea is that instead of using an IC that is filled with inverters, we can use an IC that has NAND gates, and we are going to have to use 2 of the input pins, right? We have to, that the NAND gate has 2 inputs. We're going to have to use 2 of them, but our output will do the exact same thing as an inverter. And you may wonder why, but we will get to the why in a little bit. The next one we're going to cover is the AND logic. Okay, and you know, an AND gate, it generally looks like this. Okay, so 2 inputs, and the gate logically combines those 2 with AND. So if we have two inputs, X and Y, and they go into a NAND gate. The output is then going to run into a NAND gate used as an inverter. And this logically does the same thing as a NAND gate. And if you want to trace it through to make sense of that, right, we've got X, Y. Right here, after the AND gate, we have X and Y. And then the inverter is not X and Y, which is then running twice, right? It's that value's branched in. So right here, we have not X and Y and not X and Y, and when we have an AND with itself, we get the same thing, and then that goes through the inverter, the circle, and so we get the inversion of not X and Y. And here we have the double negative, or the double bars, which cancel each other out to give us X and Y. So you can see we got the same logic of X and Y, okay, as our result after having traced through this setup. Okay, now the pencil markings, I don't want them to distract you, so I'm going to erase that. Kind of highlight this. I'm going to do the same thing up here on the inverter. That was really just to prove and kind of help you understand the why. But that's an inverter, and this is an AND gate created by, or it's AND logic created by NANDs. The last one is the OR. Okay, and an OR normally looks like this. There's a 2-input OR gate, right? So that's what we're used to using. Instead, we're going to run X into an inverter created by NAND gates. We're going to run Y into an inverter created by the NAND gate. And then the outputs of those, so this becomes really not X and not Y. Those go into a third NAND gate. Alright, and that is your OR logic. And if you'd like to make sense of it, we can trace it through, right? So this is X coming in. Now we kind of already proved the inverter up above, so if you can trust that this comes out here, right here, as not X, and that Y comes right here as not Y, then as those go into this AND gate, we're going to get not X and not Y. Okay, they have the lines over themselves, not over each other. And then we go through the inverter. Okay, we get X, and not Y inverted. Okay, and then we've got De Morgan's, break the line, change the sign. So I'm going to break that line, that top line, and change the sign. Then I've got the double negatives that cancel out, so I end up with X or Y. So that's our OR logic, right? So hopefully that makes sense just to prove. Okay, I'm going to erase this in a second, but tracing it through is just to prove that this configuration of NAND gates gave us OR logic. So the truth tables are going to match the AND and OR truth tables. I didn't write those like I did for the inverter, and you can jot them down here if you want. For the sake of time in the video, I'm not going to do that, but the regular old AND truth table is here, and the regular OR truth table would be here. So what's the purpose of this? Alright, the purpose is that normally with AOI Logic there are 3 types of gates, or 3 different ICs that would be potentially needed in making a circuit. And even if you only need one inverter, you got to go get a whole IC that houses inverters. And if you need one AND gate, you got to go grab an IC that houses AND gates. Potentially, instead of having to have at least one of each of these to create the logic, if you only have NAND gates, or just the NAND ICs, you can use those to do everything. And then often there are some simplification things that can happen to just make it so that in the end you have less ICs needed. And we're going to show that in the example. So we're going to do an example, and this is the process for NAND implementation. So how to do this. Basically, we're going to create a circuit using only NAND gates. So it says first implement the design with your standard AOI logic. Okay, then once you've traced that out using these standard symbols that we're used to, the inverter, the AND, and the OR, then we're basically going to make a substitution, or basically replace our previous AOI symbols, okay, with the NAND equivalent, which are in these boxes. We'll redraw the circuit, and then we are going to identify and eliminate any double inverters, or inversions, they say. Okay, so if you have any of these inverters back to back, right, if you have, I know it's going to be with NAND gates, but just think of the general logic. If you have X go through an inverter, it becomes not X, and not X with an inverter goes back to X. They basically cancel each other out, and so we didn't need them. So if we see any back-to-back inverters, then we'll get to cancel this out, and those are two less gates that you need. And then once we've found those, we'll redraw the final circuit. It'll be simplified. Okay? Alright, so let's go ahead and take a look at the example. If you turn the page. Okay. So, right here, we have an inverter. And instead of using a standard inverter, we're going to use that symbol. Now, you don't have to do it with A, B, and C pulling down, but maybe when you get to multisim, that's kind of a nice way to do it. So, I think I'm going to try to work straight across, though, if I can. So, I've got, and I may just put A, B, C. Okay, so I need an inverter with a NAND gate, looks like this. Okay, so how about we box that out. Then I need an AND gate, and that AND gate, I don't want to start it right here because really that inverter, the not C that comes out of that has to go into the AND gate. So let's kind of start it over here somewhere. So the AND gate, if you turn back, is the AND logic, I should say. Okay, it's the logic, but we're recreating it with these NAND gates. Is a NAND followed by the output of the NAND going into a NAND used as the inverter. Alright, so this replaced that AND gate. Alright, so going into the AND, we had the not C, which is right here. And then the other input was B. Alright, I have a second AND gate right here, ANDing C and A. So I'll repeat that same setup. We'll just kind of leave it on the same level too, if that's helpful. Alright, let's see, it was, what did I say, C. And not A. Or A. Alright, the outputs from the ANDs go into an OR. And the OR function, the OR logic, to do that, it took 3 NAND gates. Okay, the first one was the inverter one for both inputs. And then the outputs of those 2 inverters go into the third NAND for that logic. So all of this right here creates the same logic. Okay, I'm back. I had to hit pause. So there is our OR logic. Alright, the next thing we do is we look for any back-to-back inverters. And the inverters, remember, is just a NAND gate where the input has been branched off, so it's the exact same input going in. And if you can find, color's going to show up good here, back-to-back inverters, like here and here, they get to cancel each other out. And then you get to redraw the circuit without that in it. So it looks like we're going to have this, and that's C. That becomes not C. This is B. This is A and C going into another AND. And then those outputs go into another NAND gate. That was bad C. Okay, can you see that? Alright, so that is our final circuit. So we've got 1, 2, 3, 4 gates. Alright, let's think about this top problem. Alright, think about these 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Think about these ICs that we pick up. You have an inverter here, you have a couple AND gates, and you have an OR gate. So you would have picked up an inverter gate. Now, inside that you'd have 6 inverters, and you only need one of them, but you still need the chip, right? To be able to access that inverter. So how many of those do you need? You need 1, right? Then you would have gone and gotten an AND gate, an AND chip, because you need a couple AND gates, right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Alright, and you would have used, I'm counting chips here, so ICs are the actual chips, not the number of gates. You would have used 2 gates right? But there's 4 in there. You would have used 2 of the 4. Here you would have used 1 of the 6. Inverters, you only need 2 pins for a gate. With the ANDs, remember, you need 3 pins for a gate. So you would have used still not even enough to need a second chip. So you'd have only 1 chip. And then you go and pick up an OR chip. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And you only needed 1 out of the 4 that are built into the chip. So you need 1 chip. But you needed a total of 3 ICs. Okay? The more ICs you need, the more space you need on your circuit board. So they're taking up space, right? If we come down here, we have 1, 2, 3, 4 NAND gates. Okay? So if you go and get a NAND chip, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. The NAND uses 3 pins, 1, 2, 3, for each gate. There's 14 pins here. Alright, remember, one's power, one's ground. So out of the 14, we're down to 12. 12 divided by 3 is going to be 4. You're going to use 4 of 4 gates built into this 1 chip. And so the ICs, you're going to need exactly 1. And that's it. So using the NAND gates to create the logic, okay, use 4 gates but use 1 chip. That's 2 less chips. So you can get the exact same outcome in terms of what the circuit is supposed to do with 1/3 of the space on your circuit board. So I hope that example illustrates the idea of what this universal gate design is supposed to be. Okay, the universal gate, just in summary, is supposed to allow you to create the same logic, the logic we would create with inverters, ANDs, and ORs, with only 1 type of gate, with the NAND gate. Okay, and hopefully this illustrates now the power of that, is because often we end up with, in a circuit, we get an IC and we don't need all of those gates built into the IC. So this was a creative way to be able to use a tool, to use something, and to make it multi-purpose and adaptable to different logic. Okay? Alright, so that is the end of your notes. I may make a second small video to help get you started with the activity that goes along with this, which is the activity 222. It says NAND only logic design in your notebook. Okay?